Hi, welcome to Module 3 in Lecture 9. In this module, we're going to discuss joint distributions, both empirical and theoretical. In the previous lecture, we discussed joint discrete distributions. If you recall, we made these kind of tables. For instance, so we had vote and not vote. Then we had, what do we have for this one? Well, we can say education, not education. So there's one possible one here. We had joint distributions in which we had education, not education, and vote, not vote. And we used cells to determine the number of, the frequency of observations in each one of them. Right. Then if we wanted to, we could divide by the total number of observations and discover the relative frequency in each one of these cells if we wanted to. This is a way of representing a joint distribution, a joint empirical distribution across two different variables when the two variables are discrete. For a continuous distribution, we use what's called a scatter plot, which you've probably seen before, maybe multiple times. The idea is you have variable 1 and variable 2, and for each variable, you put a dot on the point that corresponds to the x value and the y value. So here's the y value, here's the x value, and so on. And you can make a whole bunch of dots and try to infer a pattern from this, and so on. It's kind of like that, whatever. That's a scatter plot. This is empirical joint distribution. It's in no way different conceptually from an empirical joint distribution with discrete variables, except instead of putting them in nice columns and rows because they're discrete, you just put the dot on the graph, on the scatter plot graph corresponding to the x value and the y value, and those x values and y values can take any value on the graph, and the real numbers. So that's an empirical joint distribution. And you'll see lots of these in your stats classes, so I won't talk too much about these. But you probably haven't seen as much before, and you won't see as frequently, but is very important for understanding statistics, are theoretical joint distributions. Now, we said already that a PDF looks like this for one variable. Well, if we're trying to understand how two variables are distributed jointly, we can use a PDF that looks like this. This corresponds to the joint distribution between two variables. If this were a PMF, then this would be equal to this. So the probability that x equals x and the probability that y equals y. So it's the simultaneous probability that the random variable x takes the value of little x and the random variable y takes the value of little y. This is what the definition would be if this were a PMF, a joint PMF. For PDF, for continuous variables, we still write pxy, but we don't have the same meaning attached to it. Instead, we want probabilities. We have to integrate over some region. So for instance, if we have the probability that x is in some set A and y is in some set B, then that's going to be equal to the integral over A of dx times the integral over B of dy f of xy. This thing is known as a double integral. You'll learn how to deal with those in part 5 of this class, but for short here, you just treat them both separately. I would integrate this one first, treating x as a constant, and then integrate this one over here with y now gone because we've already integrated out y because this is a definite integral. More concretely, we would have probably that x is in, say, AC, and this would be bigger, and y is in BD. So this would be and, these are ands, would be equal to the integral from A to C dx times the integral from B to D dy f of xy. This is again a double integral. And so you can see it's sort of the exact same thing in general as how you would figure the probability for one single variable, except now you have two variables, there's an and involved, so you have to integrate twice. once to deal with the y, and then once to deal with the x. But it's no different conceptually, it just has two variables at the same time to deal with. So these are the probabilities, and how you take the PDF or the PMF and convert them to probabilities. You do the same thing with the CDF. For the PMF, so if this is a PMF, or a discrete distribution, and the CDF is obtained by summing both of the variables. So x less than, so it's big X. No, sorry, yeah. X, little x in this case. Oh, xi, sorry. Little xi less than or equal to x, and little yi less than or equal to y, and we're summing f of x, I, y, I. So it's a double sum, and this thing equals f, capital F of x, y, which is a CDF for a discrete distribution, discrete joint distribution. For a continuous joint distribution, the CDF, as before, when we looked at CDFs for a single variable distribution, it's just the integral. In this case, instead of a to b, we have negative infinity to x. And I'll call it dx prime. Here the prime is, instead of using a z or a w or whatever, the prime tells us that we'd be integrating over the variable that's going to become x. So it's so convenient that way. Negative infinity to y, dy prime, f of x prime, y prime. And again, remember that the x prime and y prime don't mean anything. They're just the variables you're integrating over. So you can make them whatever you want to make them, whatever letter you want to make them. The important point is the x and the y occur in the bounds up here. But again, that's the exact same formula. If I were to box out this one, then this thing would just, and get rid of the x over here, then this thing would just be the normal one-dimensional CDF. With the x, I have to integrate not only here, but again over here. So I integrate it twice. Once over y, once over x, from negative infinity to x, or negative infinity to y respectively, or counter respectively. X and then y. Y from negative infinity to y, and x from negative infinity to x. So we do both of that thing. And again, you see how to do this when we deal with multiple integrals in part 5 of the class. But for these integrals, you don't have to worry about much. You just do the y first, and then do the x first, and they don't interact that much. You just treat the x as constant when you do the y. Okay. So that's a CDF for a joint theoretical distribution, and that almost covers what we want to talk about in this particular module. The only thing left are marginal and conditional probabilities, which now come into play with two variables, the same way they came into play when we dealt with multiple events in lecture 7, when we dealt with more basic probability concepts. So let's just do that pretty fast. First, a marginal distribution. If this, and I'm going to do this for a continuous distribution, the same stuff holds for discrete distribution with sums instead of integrals. So if this is a joint distribution, then the marginal distribution for y, for instance, is what you get when you average over x, when you integrate over x. So this is the marginal distribution of y. It basically takes all the values of this, right, and it integrates away all the x things, which effectively allows you to average over the values of x and see what you get left over in the y. This is the marginal values. It's the same kind of marginal definition that we talked about in the previous lecture when we had the joint empirical distribution, and we looked at how x and y were related, and how the margins at the ends of the table correspond to marginal frequencies. What we're doing here is saying, okay, for a given, forget the variation in x, what's the sort of total chance of being at relative likelihood of being at y over all x, in a sense, because we're averaging across x. So we get rid of the x here, and we're left with just y. That's the marginal distribution of y, the unconditional distribution of y. The conditional distribution is related to this in the exact same manner that we saw before when we did Bayes' rule a couple lectures ago, if this is the and, right, the joint probability in the case of a PMF, and has a similar conceptual relationship with the PDF, it's the joint probability. This is a joint probability distribution. Then we can define a conditional probability x given y times f of y. And that's a way of writing sort of iterated expectations. Sorry, iterated, well, it's similar to iterated expectations, right? So this thing right here, if you look at it, if you recall that probability of A and B was equal to the probability of A given B times the probability of B. Right? We saw that earlier. And again, you can flip A and B here, and you can flip X and Y over here. So that doesn't matter. So it's the same kind of logic. See, in this case, you have joint, conditional, and marginal, unconditional, and marginal, unconditional. So it's exactly analogous to the earlier case of conditional probabilities. We can use this thing to define the conditional probability. It's going to be f of x given y of x given y. It's going to equal the joint probability divided by f of y given y. This should look very familiar from how we derived Bayes' rule back in a couple lectures ago, and this comes up a whole lot in Bayesian statistics as you deal with posterior probabilities and conditional probabilities based on observed data, and other things too in stats. It's a fairly important thing. It won't come up a lot more in this course. This is here mostly to show you how it works. For when you do take your stats classes, you'll have some experience in seeing this stuff. But these are different ways of writing joint and conditional probabilities. We're not going to spend a lot more time on joint probabilities in this course. The rest of the lecture will be on single variable distributions. We'll talk about multiple variables in part 5 of the course, and there I'll discuss a little bit multiple joint distributions in the context of multiple integrals. But you've actually seen most of that already here. There's not much more going to happen. So this is mostly what we're going to talk about. So this is most of what we're going to talk about involving joint distributions and multiple variables in distributions. Again, you see a lot more in your stats classes. This just gives you a sort of a taste, a flavor for what you'll be seeing and where it comes from and what the sort of background of it is. But again, the important point to remember here is that all the stuff from more than one variable follow pretty directly from looking at one variable, and pretty directly from all of the basic rules of probability, right? The Bayes rule, the definition of and, transmit directly to looking at joint distributions and conditional probability distributions, which are related directly to conditional probabilities. They're all very similar, the same ideas hold, so just because there are more than one variable in these distributions doesn't mean we're learning anything particularly new. It's the same ideas, again, just with a little different notation applied to distributions as opposed to probabilities, but it's the same thing. And that's it for this. The next module, we're going to talk about expectations more generally and introduce the uniform distribution. Thank you very much.